So in this course, I want to briefly describe on which topics we are covering here and what is relevant, what is this course actually about, because a substantial number of you may have no idea what photogrammetry is. So photogrammetry has something to do with light. So the word pho comes from the Greek word light, and gram refers to as written or being recorded. So photogrammetry is, in the end, means we are measuring with light or drawing with light. And so that means we are actually using cameras or camera-like sensors to perceive the environment and then use this as a measurement device to then draw conclusions out of this or perform estimation tasks. Again, it doesn't have to be cameras only, it can also be other forms of electromagnetic waves like a laser rangefinder, although here in that course we will mainly focus on cameras, either single camera systems or so-called stereo camera systems, which are basically two cameras mounted next to each other, similar to our human vision system, which is also a stereo vision system because at least most of us have two eyes that are operational and which we use to perceive the world around us. So photogrammetry relates to the estimation of geometric objects as well as semantic properties of objects or the world around us using images or observations from similar sensors. So this is one of the definitions of photogrammetry. And you can see important elements popping up here. Estimation, so it refers to that we do kind of state estimation problems. It says we are interested in geometric properties as well as semantic properties. So geometric properties are things like what's the size of a certain object. Semantic properties means what kind of object that actually is. For example, a building, a tree, a human, a car, or things like this. And we do this based on images, so in this case camera images, or based on observations taken from similar sensors. As I said before, this can be a camera which also provides depth information. This can be a laser scanner, sensors operating with electromagnetic waves, for example. So the definition is a little bit foggy. So these what are similar sensors does not only include cameras, but the course here will mainly focus on cameras. So what are now these different geometric and semantic properties? I brought you two examples. So the key problems in photogrammetry is one, estimating geometry. This can be seen here. What we see here is actually a building, the Frankenforst building, that is owned by our faculty. And what we can see here is a number of red points. And these red points are the 3D location of points that have been estimated from a UAV flying around and taking camera images and then trying to estimate where the to which point in the world an individual pixel corresponds to. And you can see that those red dots here lie on the surface of the object that has been inspected. And this is one form of geometry estimation. So we are estimating the geometric structure and properties of that building. The second part is a semantic interpretation. That means putting meaning to pixels, assigning to each pixel or each object that we see in an image what it actually is. So in this example, this is a picture of plants on a field, in this case sugar beet plants. And what we see here, so this is the input image, and what we see in the output image is basically a color mask. And this color mask tells us what kind of object we are seeing. So green means in this example, this is kind of the sugar beet plant, in this example, the plant that we are interested in and inspecting. And the red plants here are actually weeds. So plants we actually don't want to have in our fields most of the time. And so by this semantic interpretation saying what is important or what is relevant, what is value crop in this example, and what is the plant we don't want to have in our field through green, illustrated here through green and red, we can actually decide what is the weed pressure, for example, in a field, and then take even automated intervention actions using, for example, an agricultural robot. So this is geometric estimation, where is something in the world, and the semantic interpretation, what is it, what I'm actually seeing in that world. And this is actually what's the short summary of what do we actually measure, and now getting a little bit more precise on what we actually will look into this course. We will look, for example, into camera localization. So given I'm observing a scene with a camera, can actually estimate where the picture has been taken of that camera. This depends what I know about the environment. If I know something about the environment, I can typically localize the camera. But even if I don't know anything about the environment and have multiple camera images, I can still say something at least about the relative movement of the camera. If you know where a camera is located, we can also estimate where are certain objects in the environment. based on a single image, that can be a little bit tricky, and we may not be able to derive the full information, but given multiple camera images, we can do this and can actually build a full 3D reconstruction of the environment. That means estimating the whole 3D structure and estimating the location of all relevant points in the scene. In order to do that, what we often need to do, we need to have measures of similarity. So if I see something in an image 1 and see another object in image number 2, making the decision, is this actually the same thing? Is this a similar object, or is this the same object? Do those pixels look similar? Yes or no? And this is an important question which we need to do in order to find so-called correspondencies. So seeing something in image 1 and seeing the same thing in image number 2. And this is important, for example, for doing 3D reconstructions later on. We are maybe interested in detecting object. What is it what I'm seeing? Finding all persons in a room, or all cars on a road, or all buildings in a map, or in an aerial image, which I use to create a map. These are things where these object information is relevant. Or semantic interpretation, so that I'm adding semantics to the scene, or semantic segmentation. That was the example of the plans that I've actually seen before. So we are here at the intersection of several disciplines. So first thing is traditional photogrammetry, often used to build maps of the environment, but also has gone through a large number of changes in the recent years. Computer vision is a field which has grown a lot over the last 20 to 30 years, and is actually by now much larger than the photogrammetry community, and does a lot of relevant works that are relevant for us. For example, for doing 3D reconstruction, for doing semantic interpretation. Also today, machine learning plays a larger and larger role. Whereas 20 years ago, you mainly needed machine learning for doing some interpretation tasks, and it was kind of not that frequently used. By today, a large number of problems that we're tackling here are using machine learning techniques, as they are very powerful tools, especially for the semantic interpretation, but even for solving certain parts of the geometric reconstruction task, we find learning techniques being used today. And also robotics is extremely relevant, because robots and autonomous devices, this can be robots driving around in our environment, solving logistic tasks. That can be UAVs flying around in the open space. This can be autonomous cars driving around. These are all systems which automatically or autonomously, so it means without human interaction, do certain things and need to interpret their sensor observation in order to do something useful. And so we are here in this group among those 4 disciplines, doing work in photogrammetry, doing work related to computer vision, using machine learning techniques, solving robotics problems. So that's something that we are here sitting somewhere between those 4 disciplines. And the course here today will be an introduction into photogrammetry, but a lot of concepts that we see actually stem from the computer vision community. We will use machine learning algorithms here to solve certain tasks, and have certain robotics application in mind, for example, with respect to online state estimation, which are relevant if you want to have a system which makes decision based on what the system is actually seeing. So again, photogrammetry has a lot of connections to other fields. It's basically what I explained to you before. It started for surveying purposes, then remote sensing became a central part of photogrammetry, then basically remote sensing became an own discipline. Image processing plays an important role, and with the upcoming of digital technologies, digital cameras, computer vision was playing a larger and larger role. It's an extremely large community by now, larger than the photogrammetric community by far, and has very strong links to state estimation problems, for example in robotics, in computer vision, for semantic interpretation tasks, machine learning. These are all kind of an interdisciplinary field, or as tightly coupled fields addressing very similar tasks. Maybe with different applications in mind, and then every community has its own kind of particular focus, for example, on properly estimating all the uncertainties, taking that into account, or other fields look more on real-time approaches. There are different flavors of the used estimation techniques, but overall these are fields which have a very, very big overlap. I want to now come back to cameras and say, why are we actually using cameras? What are advantages of using cameras? The first thing which is interesting is that we can do contact-free sensing. So why is contact-free sensing a relevant thing? This has a certain number of interesting properties. If I can do contact-free sensing, I don't need to be able to access objects. It's just enough and I see objects, which can be different. So I can have access to inaccessible but visible areas and perform measurements for those objects. This can also be important if this is a very sensitive material or extremely hot or extremely cold or toxic materials, things that I don't want to touch or can't touch, I can still access with contact-free sensing. And cameras are an interesting tool, an interesting sensor in order to do this. What also is good with cameras is relatively easy to acquire large data sets. We have cameras which can take images at very high frame rates. I basically need to walk by, drive by, or steer a platform to get a sequence of images, and based on the sequence of images I can actually perform a lot of state estimation tasks. It also provides a dense coverage of the object, so we typically have a large number of pixels and it's a whole area which is covered, which is different from several other sensors. The data is also generated at a rather high frame rate and has flexible resolutions. So if I go closer to an object, I automatically get data at a higher resolution, and if I'm further away, I have a lower resolution but can cover objects with a smaller number of images. So I'm very flexible in this data acquisition process and can use this in an interesting way. In general, cameras provide 2D information in the sense that they take the 3D information and project it on a 2D image plane. So some information, in this case the depth information, is lost in this process, but I can still recover this depth information if I have multiple images taken from different locations. And under some assumptions I can do full 3D reconstruction, so I can perform 3D sensing, although the sensor provides basically only kind of a 2D image plane at the moment. There are other things which are really important. If I can capture images with a high frame rate, I can also capture dynamic scenes, so things which are changing. I can document changes. It's more than just a geometric measurement of just measuring certain distinct points, because I can also perform a semantic interpretation. Especially modern machine learning algorithms allow us to interpret image data in a very attractive and very versatile way, and allows us to infer what we are seeing, automatically derive descriptions of what's going on. Another advantage is that we as humans are good at interpreting images. So it means we are trained through our eyes of taking image data and interpreting images. That means data which is collected from a technical sensor such as a camera can still be very well inspected by a human operator to see if the data looks good, or if we have some other problem in the data acquisition process. And the images itself document the data acquisition process, which is something which is very attractive if I have access to sites only, or to measurement sites only for a limited amount of time, and I need to get data out there. I need to make sure this data is in the appropriate format there. The data is usable for the measuring purposes and not through a sensor failure, for example. I take my equipment home and realize at home that the data is unusable. That's something which is rather easy to verify using camera systems. However, there's no free lunch, so also cameras have certain disadvantages, and we should also be aware of the disadvantages of those systems. So the first probably major disadvantage is we actually need light to take images. This sounds a little bit, it's clear, but it sounds a little bit weird, but if you think that half of the time we're living in darkness, that means we can only use our cameras 50% of the time, unless we bring an artificial light source or flashlights or other things. So lighting, external lighting is needed in order to take good images. The other thing is that cameras don't really measure object, they basically measure intensities of reflected light. So sunlight shines on an object or an artificial light source, the object reflects that light, and then we measure that light. So we're only measuring intensity values, we're not really measuring precisely points. Through the dense pixel grid, basically every pixel in an image corresponds to one direction, to one ray. So we know what we are seeing, actually, that there was an object reflecting a certain amount of light at a certain wavelength, which gives us color, into a certain direction. That's basically what the camera provides us. That means occlusions play an important role, because we can't look behind objects. And the 3D world is projected onto a 2D image plane, so that only the closest object is actually seen and the depth information is lost. And that's something that we struggle from substantially if you want to do 3D reconstruction, which is a central challenge in photogrammetry, but also in geometric computer vision. And there are also certain measurement devices which provide us with higher accuracy, but cameras actually are not too bad, especially real high-resolution cameras. So if you think what cameras measure, we see that cameras basically measure directions. So this is just an illustration. So this should be the real world, and this should be kind of the image. This is the projection center, so a single point where all rays pass through. So every pixel basically corresponds to a ray which passes through the projection center and then into the real world. So in this case, the reflection of the sunlight on the top of that mountain will be redirected on this location in the pixel. So this intensity value is the reflection of the sunlight of that mountain peak in this example. So every of those pixels basically corresponds to one ray through the environment. And this ray, we just measure not really the object which sits there, but just the reflected light, the intensity of the reflected light. That's what we're actually measuring. But by exploiting those intensity values, we can, of course, find locally distinct patterns and then try to match patterns, for example, between images. But first of all, it's just a certain intensity in a certain direction. If we now want to go for 3D perception, which is something that we're going to do in the Photogrammetry II course, we can take multiple observations from different locations to actually extract 3D information. So as an example here, given we know the locations from where the images have been recorded, so this is image number 1 and this is image number 2. If I now know that a certain pixel in image number 1 corresponds to a certain pixel in image number 2, then I can actually perform a triangulation, so basically take this ray, shoot it from the projection center through the image in the 3D world, the same here, and where those rays intersect, I know that this object must be here. What I need to do in order to perform the 3D vision, I need to have multiple images taken from different locations. I need to know those locations, and I need to know which pixels correspond to each other. But if I have this information, I can actually extract 3D information out of these individual 2D images or pairs of 2D images. So the camera in the end is a device which performs mapping from the real world into an image. So if you think to the mapping from the real world or from an object to an image, we have an object which has a certain geometry, it has a certain location in the world, a certain type, and we have a camera as a physical object which has certain properties like certain intrinsic parameters, so the inner parameters of the camera. The extrinsic basically means where the camera in the world. And then we have this magic thing called physics, which turns object plus our use of a camera into an image. So this is what physics does for us. The guys who invented the cameras basically apply principles of physics to turn the object that we see in the world using the camera into an image. Okay, in photogrammetry we typically have that image and want to actually do the inverted process. We want to actually estimate something about the object or about the camera. So we have that inverted mapping in photogrammetry. That means we start with images or an image. Of course, we still know physics exists and we know things about physics. And we have certain background knowledge. We make certain assumptions about the world or know that certain data points have been captured in a certain setup. And this comes together into some form of algorithm, some form of kind of description on how we need to use images, background information, and physics to infer something out of that. So this is basically the algorithm, the description, the handbook on what to do. And this allows us to infer information about the object and about the camera so that we can estimate the location of the object or the extrinsic, so the location of the camera, or some intrinsic parameters of our camera. So we are working in this invert mapping. Starting with images, knowledge about physics and other background knowledge, and at the core we are developing those algorithms there. So this is the key part that we are doing. This is where we are in order to provide us information about objects and camera. And these algorithms may be things which allow us to estimate semantic information or estimate geometry information. And so this algorithm, this description of an approach which allows us to turn images into other information, this is at the core. And we can actually relate that to a form of human perception. So what happens typically, we have an object which is observed by our eyes, which is kind of our sensor. And then the information from our eye goes to our brain, and the outcome is an interpretation of the scene. For example, estimating us where objects are located or what an object we are seeing. So from the object to the interpretation through eye and brain. And so the question is now, if we see it from, which is interesting for us, from the point of view of the field of photogrammetry, is what is actually the more tricky part? Who does most of the work? The eye or the brain? So is it more tricky to turn the object into kind of an image-like structure, or is it a trickier problem to interpret what we are seeing and put that into meaning? And in order to answer this question, we can of course have a subjective view of who does more work, eye or brain, and can argue about this. We can actually do an experiment and maybe make this information. Because we know it's hard to go from object to interpretation, but the question is, what's the more tricky task? Human eye or human brain? So seeing or interpreting what we are seeing. So what we can do is we can do an experiment, and we take a person who's blind from birth on. So the person has never seen an image with their own eyes. So basically the person has no camera. So what we can do now, we can take an artificial camera or kind of a regular technical camera and take an image, and instead of showing the image to the person, which we can't do, or not directly, we can actually print the image on the person's skin. So printing in the sense of having a device where every pixel with a high intensity value stitches to the skin a little bit, and where it's dark pixel, we have a different effect or have no effect there. And so then we have the human and this device on their skin, and the question is, can that person see? So what does seeing mean? So can the person do the interpretation that we point the camera to an object and the person can tell us something about the object? And it turns out, after some training, yes, you can actually do that. That person can, for example, recognize different objects which are shown in the scene. So as a conclusion of that, the eye is definitely useful, but the majority of the work seems to happen in the brain, because we can replace the human eye with a camera, and even though the person is blind from birth on, so has never experienced eyesight, the image data put through, let's say, different sensor device like the skin can be used to actually make the same or a similar interpretation of the scene. So as a conclusion for that, designing the sensors is not what we are focusing on. We focus on doing the interpretation, so taking the sensor data and build the algorithms that allow us to do the estimation. So algorithms are central in here, and they are a key ingredient. So for estimating semantics or geometric information from images, we require brain power, and our algorithms are the central element in here that kind of describes this brain power. And as a result of this, also algorithms and software development plays an important role in here. Building software or building algorithms, and at least having a basic implementation of this algorithm, is a key ingredient in order to verify assumptions, in order to build our algorithms, test our algorithms against real world data. And therefore, being able to implement certain solutions is key for understanding them and for actually working with those solutions. And as a result of that, programming is something that is important in this course, and we will guide you through the process of supporting you to help you to learn to program. I mean, you had some programming experience in your courses already, but not necessarily with Python, so we try to support you with this as good as we can. But being able to program at least basic things is important for the understanding, and you should allocate some time, invest some time in order to do that well, because it is a tool that you will use in the future more and more and more. So all the activities that we are doing, for example, in our lab, all have to do with programming. It doesn't mean you need to be the excellent coder, but it's like a tool like writing and reading. If you can't write and read, it's very hard to study. And similar things hold for programming. It is an essential tool for solving relevant problems. Okay, then I would like to very briefly talk what are typical sensors used in photogrammetry. And we will, as I said, mainly use cameras here. So these can be standard industrial cameras that you're using here, but also standard consumer cameras like your SLR or your mobile phone are cameras that we can use for acquiring camera images, and then we basically work with those camera images. We don't really care from which camera the data is coming. We may want to know, let's say, what kind of lens was used, what are the parameters of those cameras, and of course there are cameras which have a higher quality or a lower quality, but overall it doesn't really matter which camera we are using here. Another sensor is, for example, this is a very large camera using also different bands. It's the Microsoft UltraCam used to build Bing maps or parts of Bing maps, which is basically an aerial camera that it sits in an airplane and takes images from near nadir view looking downwards of the Earth. So if you use, for example, Bing maps, they have been created using also this camera data. Other sensors which play an important role are laser rangefinders. So these are sensors which send out an electromagnetic wave, so a laser ray, and wait for the signal to return and measure the time it takes. So they provide us distance information. Compared to cameras, it's an active sensor because it actively sends out light and waits until the light returns. And through this provides us with distance information. So the sensor data is somewhat different that we get from a laser rangefinder. Compared to a camera, a laser rangefinder plays an important role, but not that much in this course. Here we are a bit more on the traditional side and mainly look into cameras for, let's say, 95% of all our examples that we're using. So what are those examples? What can we do with photogrammetry? So one thing is we can actually build maps. So the first thing is if you have this map, for example, Google Maps or OpenStreetView, you can use photogrammetry to actually build those maps. For example, using aerial images or images from satellite data to actually interpret those images and turn them into maps. So you may have a view which looks like this, and I can run automatic algorithms which interpret what they are seeing in these aerial images, identify streets, for example, and turn that into map information. And we will look into that not necessarily from the semantic interpretation point of view, but from the geometric estimation point of view. How can I turn, for example, aerial images in a map or a new image so that I can actually measure in those images? Something which are called orthophotos, something that we are going to do, for example, in the Photogrammetry II course. We can also estimate the full 3D information, like terrain models of different environments or of natural places. We can actually use our techniques for performing 3D reconstruction for performing this estimation. We have environment monitoring applications. So what you see here is a UAV equipped with cameras, which in this example flies over a field near Bonn here in Klein-Altendorf, and we can perform monitoring tasks. So we can interpret the image data that we are seeing, and we can, for example, observe the field and then say, okay, here we see in green again value crops, and in the reddish color here we see weeds, so plants that we don't want to have in our fields. And through this automatic monitoring, we can actually trigger field management actions just by interpreting this data. And this is something which plays an important role here in Bonn, as we're heading one of the clusters of excellence, PhenoRob, Robotics and Phenotyping for Sustainable Crop Production, where those techniques are developed, for example, using UAV technology or using ground robots. We also have been working here in the Institute at the IGG a lot with UAVs and had larger projects involving several people from our institute as well as from the computer science department for building autonomous drones. So this was a project Mapping on Demand as one of the examples that you can actually see here. And so what you see is a UAV which flies over the environment, and you see here a trajectory estimate which is done here using GPS and IMU information. At that point in time, this is the work done by Heiner Kuhlmann's group for estimating the trajectory of that UAV. And then we can also use camera data to enrich the sensor data with camera information. In this case, these are 2 stereo cameras and a high-resolution color camera as a monocular camera, and then perform aerial mapping using this data. That means we can extract features or kind of distinct points in the environment and then track those features over time to estimate where the UAV is actually flying, and can enrich the GPS and IMU information with this visual information. So it means we can see this here through these illustrated here in green, this reference frames where the orientation information also using UAV can be estimated. So even if we have, for example, GPS outages, so the GPS fails, we can still use the visual tracking system to estimate where and how we are flying. So in this case we have a GPS outage, and we can see here that we can actually continue the track estimating where the UAV is flying without having this GPS information. And even if GPS comes back after some time, we are today able to perform highly accurate GPS visual odometry information that we basically can track the position without having substantial inconsistencies or jumps in this mapping process. And this allows us to estimate where UAV is, where the cameras are, but can also allow us to estimate the position of the UAV. And then we can exploit this information to actually perform a mapping task. So we can also use the information about what we are seeing in order to estimate the location of 3D points in the world. So this is basically this Frankenforce building, what I was showing before, and this is a similar data set to the one which was used. And we can see here that the mapping process started, in this case, extracting features of the environment and estimating the location of points on the scene. And what runs here is a so-called bundle adjustment approach, which is a least squares approach for estimating the camera location as well as the location of distinct points in the environment, which then allows us to provide, after some optimization, a full point cloud of the scene, which I can also compare to a high-resolution 3D model and can see that those points are very close to the original model, typically with errors of 1 to 2 centimeters are possible to obtain with those UAVs. Other examples are orthophotos, something I explained before. So this, what you see here, is an image. It looks like an image taken from very, very high above, which is corrected in a certain way that we can actually perform measurements inside those images. And this is something that we also use here in photogrammetry a lot to make those corrections to images in order to build maps from aerial data. We do not only need to do this from aerial data, we can also do with mapping vehicles. This is an example of a video by the group from Luc van Gool and his spin-off Geo-Automation in Leuven. What you see here are camera images taken from a mapping vehicle, and you can see now that the vehicle is actually equipped with multiple cameras. In this example, 8 cameras, 2 pointing forwards, 2 pointing backwards, and 2 pointing to each side, so that we can observe the same part of the scene. And by knowing how those cameras have been displaced, we can actually estimate 3D information and can then estimate a point cloud of the objects that we are seeing in the scene. You can see this here, how we're moving through the environment. All those dots you see here in the background are points that have been estimated from this camera information. And these surveying vehicles allow us to accurately build maps of the environment of whole cities or whole countries, just by driving through the environment, recording the sensor information, and building 3D models of the scene. Of course, for building models of that size, you will require additional information. GPS information is also used, but you can actually build large-scale maps of the environment so that you then can actually go back to those models and then also generate virtual fly-throughs through those 3D models or point cloud models. All this becomes possible using this technology. You can also use this information to build 3D models. So this was an early work done by Fu in California, building 3D models of environments by having camera data or also laser range information. And we see today, so this is an example from Berlin, already a few years old, how certain parts of the city can be reconstructed from different sensing modalities using aerial image data, using laser range data, and being able to provide full 3D city models, which is today provided for much more cities than just Berlin, which was the case maybe 5 or 6 years back when I created that slide. Other applications are digital heritage preservation. This is a work that part that I've been working on. What you see here are catacombs, so big underground structures, very popular in Italy, in Rome, for example, which are of high cultural relevance. And this is our very big kilometer-long tunnel systems. And we can use robotics technology and photogrammetry to actually do 3D reconstructions. We can, for example, build a robot and explore those environments with the robot platform. So what you see is a robot. We have a couple of camera arcs, 7 cameras are sitting here together with light sources, and we can navigate with those platforms through the environment and record sequences of images and then performing 3D reconstructions of images. So what you see in here are basically always 7 images, basically 1 image from every camera, and this is kind of the time domain while we are driving through the environment. And you can use this and use these 3D locations that we are estimating to do 3D reconstructions, so that in the end we can obtain 3D reconstructions just from these camera images which look like this. So these are photorealistic reconstructions of the scene. So the blue thing stems from occlusions because the robot was driving very close to the ground, but you can do high-resolution 3D reconstructions of the environment using this technology. And this is one of the examples which you can use for building 3D models of these cultural heritage sites, and then, for example, also plan intervention missions in those catacombs. And this here is, for one example, the Catacombe di Priscilla in Rome, and this is a part of this catacomb which has been mapped over actually several hours. So it's a very large multi-floor catacomb system that we can map using the technology that we will also discuss and develop here in that course. Another big application area is robotics. That's something that I've been working on and I'm still working on since nearly 20 years by now. And so this can be things like your robot which cleans your floor, a lawnmower, can be an autonomous car, can be tour guide systems, can be other research platforms for navigating through the environment. So there's a whole variety of different autonomous platforms that uses this technology. One example is in a street scene. So we may want to perform visual localization estimate. Is this what we see here in the same place? So we have one image here on the left-hand side and one image on the right-hand side. And you can see that it visually looks very similar. So the question is this actually taken from the same place? And it turns out, yes, this is actually the case. The only difference is one was in summer and the other one was in winter. And so the appearance of the place changed. So you need to have, in order to solve this image matching problem, you need to solve, or to do this localization, you need to solve a challenging image matching problem. This can also be here. These are always pairs of images which are identical: summer, winter, night and rain, overcast during the day, sunny versus not that great weather. And so performing this image matching, relating these images with each other, then can allow us to actually localize. And this is an example from image sequences, also work done here in my research group by Olga Wysocka on estimating the correspondences between those images and then localizing the images here from the sequence data. So what you see here is where the current image is, and this is basically the previously mapped trajectory in winter, and you can also see with this yellow dot here where the platform is. At some point in time right now we don't have a match because the system is actually outside the mapped area. But as soon as the system re-enters, we're actually able to make those image correspondences and then actually localize in the previous image stream, which allows you to make data associations between places where the appearance has substantially changed. Again, this approach here uses the sequence information in order to perform this high quality place recognition, but there's just one example of what you can do. In general, robotic cars play an important role. So what you see here is one of the first that's actually not true. It's not the first autonomous car, but the first car which led to the second boom of building autonomous cars. It was the Google car that was developed by people around Sebastian Thrun, who also worked on the DARPA Grand Challenge a few years before, building one of those vehicles which can autonomously navigate through the environment. A lot of the perception in this first vehicle works via the laser scanner, which sits here on top and observes the scene. So this is kind of what the scene could look like. So you can see here, estimate or guess where the curbs are and how the vehicle may move through the environment. And so while the vehicle is driving, it gets this perception, actually need to steer how it can go. So this image is approximately 10 years old by now. And if you look now to updated material, for example, from Waymo, which is right now the company working for Google, building those images, I have an example what today's systems can actually do. So you can see a 360-degree view of
Back
the environment.
In 2009, in our early days at Google, we started working on self-driving cars. Today, we're called Waymo, and our fully self-driving cars are on the road. They use a range of technology we've built from the ground up to understand the world around them and get you where you need to go. You're about to see how it all works and what it feels like to ride in our car. As it drives, Waymo uses LiDAR, which sends out millions of laser beams per second to build up a detailed picture of the world all 360 degrees around it. It also uses radar to detect how far away objects are and their speed. And high-resolution cameras detect visual information, like whether a traffic signal is red or green. It then combines all that data to understand the world around it. For example, in this fraction of a second, it knows exactly where it is on the road. It can also identify everything around it in full 360 degrees, and then predict what those things might do next. And it doesn't just do that for the objects you and I can see.
So what we can see here in this video is a lot of the things that I have discussed before being integrated. So we have different sensing modalities such as camera information, LiDAR information and radar information, which are used to solve different parts of the geometric state estimation problem. So where are we, where are other objects around us? And it's a semantic interpretation problem. Is that what I'm seeing there? A car, a pedestrian, a cyclist? And then uses information and knowledge about how those systems typically behave and how the rules on the road are, predict what those other objects are doing in order to then plan their own motion through the environment. And the video goes on for a while and explains a couple of those concepts, but what you have been seeing in this first video is how the different technologies that I've discussed here before, at least very briefly, come together in terms of perceptions from camera data, laser range data, or radar data in this example, being fused together, performing state estimation about geometric properties, semantic properties, exploiting map information, combining this with map, localizing a camera, object detection. All those technologies come together to actually solve the self-driving car problem and navigate through our world in autonomous fashion. So the photogrammetry module, which consists of the two courses, Photogrammetry 1 and 2, is intended to provide you with the foundations of photogrammetry and state estimation and interpretation techniques that are building blocks for developing several interesting and exciting applications. So the application that we have seen here, building autonomous cars, building autonomous robots, performing observation and monitoring tasks, building autonomous UAVs, these are all things that we can do given the technology which is out there. Again, this brings me also to the end of the course. I designed the course in a way that the slides are actually self-contained material. So I think you do not need more material than what I'm presenting here in the videos and what is explained in addition to the slides. Nevertheless, if you want to look up more material, there are a few things you may want to look into. The first thing is the Hartley-Sisson and multiple view geometry book. It's kind of the Bible on multiple or on 3D reconstruction using cameras. It's a very good book. It's one of the standard references for performing state estimation. It's not always an easy read, though, I have to say. Then there's, for the aspects related to machine learning, the Alpidin Introduction to Machine Learning, which I found one of the best books, introducing machine learning concepts in a way that everything is first done in 1D, explained very intuitively, and then generalized to multiple dimensions, which I found when I was learning machine learning one of the best books that I experienced myself. Zielinski Computer Vision Algorithms Application is also one of those standard reference books that you find out there. Also Wolfgang Förstner's Photogrammetric Computer Vision book may not be the best choice as an easy read, as an introductional material, but is a very good reference material. There exist old scripts from Wolfgang Förstner times here at the University of Bonn, Scriptum Photogrammetry I and 2 as well. I'm deviating from the material to some degree. Some of the material is covered in the course. I took the notation from the script, but you can perfectly do it without that script. and you should be able to go through this course actually without additional material than except that what is going to be presented here. With this, I'm coming to the end of my introductory lecture here today. I hope we stimulated your interest in photogrammetry and related topics, and the next steps are, as I said, the introduction to Python and bringing you closer to hands-on experience, implementing basic computer vision algorithms and photogrammetry algorithms, and this will be done by Jan Weiler and Louis Wiesmann this year, and then we will start after this introductory part with the techniques, the technical aspects of photogrammetry, where you then use those programming techniques. With this, I thank you very much for your attention and looking forward to see you soon. Thank you.